Hello everyone, my name is Nguyen Luan. Today I will introduce for you about my research topic, a multi-source data fusion framework for electric vehicle charging duration prediction. This research is under conducted by Supervisor Dr. Dakwang Anh. This research have four main sessions. One is the introduction, two is the material and method. Three is result and discussion, and four is conclusion. Now we have to go the first part, introduction. As we know that the pollution and climate change are rising sharply, and is by gasoline vehicle. And a gasoline vehicle generate nearly 30% of the greenhouse gas emission. To address this, we have to urgent shift to net zero transportation, and that is a electric vehicle. The electric vehicle has two main barriers, is range anxiety and two is the high stress on grid. First is range anxiety. The past research have proved that 187 87% 87% of daily needs are met by the current tech. And in the figure two, we can see that the electric vehicle in the Asia Pacific has increased sharply, and this lead to the high stress on the grid. And to address this, vehicle to grid to has show potential to decrease the stress on grid, but it's very uncertainty regarding user behavior and connection times. That we don't know the exactly time the user charge on and discharge the vehicle, so that we have to accurate the prediction of electric vehicle charging duration. In the past, we have two research to predict the charging duration. First is based on a physics-based model. This is by this publication by Gonzalez, Shane, and Becerra and Zhang. But the limitation on this publication is rely on the complex and inaccessible internal parameter, and is often too theoretical. And the two publication is based on the traditional data-driven model. This publication is published by Magic in 2024, but this have a limitation that the chit-chatting data as an isolated time series. So to address this, in 2025, Alaja indicate that the future of forecasting lie on multi-source data integration, not just algorithmic complexity, like two publication below. In my research, the objective is analyze the impact of multi-source data fusion on the accuracy charging duration prediction. And we have three input variable. One is a historical charging log. Two is the real-time weather condition. And three is traffic status. And we have to analyze this comparative with between five algorithm. One is linear regression, two is random forest, three is gradient boosting, for ECG boost and light gradient boosting. And we use and I use matrix MSE, MAE, MAPE, and SMAPE to evaluate. And the goal in my research is identify the optimal machine learning models for practical and real-world deployment. Now we change to the session 2 is the material and method. First, I introduce you my case study. This case study is located in the Chohem. This include include 2,400 resident across 1,180 30 apartments, representing a large-scale residential complex. As you can see in the table 1, on the table 1 key information on the case study, the apartment and in table 2 we have the charging session from December 2018 to January 2020. These datasets capture total 6,878 charging session from 87 unit user, and it is recording between December 2018 to January 2020. And this research objective and the objective to case study is enhance electric vehicle charging duration accuracy, and identify the optimal algorithm through the rigorous comparative analysis of machine learning model. Now, we change to the research framework. This research framework include 5 steps. One is data preparation. I will clean the raw charging logs and apply one hot encoding to remove 5% outlier using isolation forest, and I split 80% to train and 20% to test. Step 2 is a baseline training. We train regression algorithms on historical data only to establish a bandmatch. The step 3, we are merging the data. We fuse the weather. I fuse the weather and traffic with charging data via timestamp synchronization. And the step 4, we retrain all algorithm on the multi-source datasets to capture nonlinear environmental correlation. And the final step, we benchmark model and assess the specific impact of the external data. Now is the research content. As we know that the charging data is the high dimensional data with more 5,000 features, and this very sparse. And this and my dataset is structured the tabular data. So why I use the ensemble learning? in a 2022, it, the Greenstein and Schwartz indicate that the ensemble learning is outperform deep learning outperform in data with Thai tabular data and Spark. So we used ensemble learning. We choose 5 algorithm that first is a linear regression. Is that the baselines to validate the complexity needs and backing and boosting. In the backing, we choose the random forest to reduce the variance. And in the boosting, we choose 3 algorithms like gradient boosting, EG boost, and light gradient boosting to reduce bias and handle sparsity. Next, we go to the theoretical to a background of a selective model. Like what linear regression attempt to fit a simple line and backing view tree in parallel while boosting view tree sequentially to correct previous error, allowing it to capture complex nonlinear Persian. In the linear regression, the minimize residual sum of squares and via ordinary least square. And random forest arrays a declarated trees using bootstrap sampling and random subspace method to reduce variance. Gradient boosting iteratively train weak learner to correct the shadow ratio of predecessor. HG boost is used second order Taylor approximation and sparsity aware splits fighting for zero value entries. And light gradient boosting is focused on efficiency using the leap-wide growth and a gradient based one-side sampling for high speed. Now we change to the session 3 is the result and discussion. In step 1 is data preparation. We remove 343 anomalies, and the final data set is a 6,501 records. We apply a one hot according to categorical features. And we can see that table 3 is the data cleaning. The total set 377 anomalies. And in step 2 we have establishment and baseline training. As we can see in a figure 8 performance comparison of baseline model, and in the table 4 result of baseline training, we can see that gradient boosting achieves the best performance with the lowest MSE, and validating its ability to model complex nonlinear behavior. Conversely, linear regression failed catastrophically due to perfect multi-collinearity caused by one-hot encoding. This confirms that tree-based ensemble handle high-dimensional spaghetti effectively. Now we go to the step 3 and step 4. And in step 3, we have data merging. The charging logs was synchronized with weather and traffic data and cleaned to retain 6,844 valid observation. And we create a matrix one hot encoding expanded the feature space from 55 to approximately 5,000 variable. And this result is a highly sparse and high dimensional design matrix. And step 4 is establishment and baseline and baseline multi-source integrated chaining. We can see that contrary to the expectation, we integration exogenous variables degrade performance across all models due to the cost of dimensionality. The gradient boosting remained the top performer, but suffer 18% MSE increase, while linear regression failed catastrophically. The expansion to 5,000 smart feature introduced excessive noise, overwhelming the predictive signal from weather and traffic data. And the final step, we comparative analysis and impact assessment. One is a horizontal cross algorithm benchmarking. As we can see that gradient boosting outperform all peer in the bold phase in the baseline and integrate, proving its robustness against high dimensionality. And algorithmic is a sequential residential collection mechanism prove more effective for this sparse dataset than the random forest parallel packing. And we prove that the nonlinear conformation, the failure of linear regression rule out linear model for capturing complex EV charging dynamics. And we have a vertical impact assessment, gradient boosting, performance analysis. The MSE gradient boosting, it already rated by 18%, and SMAPE is escalated from 61% to 84%. This confirmed that the excessive noise from 5,000 smart features overwhelm the environmental signal, and proving the necessity for feature selection. Now we change to the finally session is the conclusion. The key contribution is successfully establish a standardized pipeline to synchronize three data sources. Validated that gradient boosting offer the best stability, while random forest achieve the best precision. The failure of of the linear regression confirmed the complex and nonlinear nature of electric vehicle charging behavior. And we indicate the critical insight that the cost of dimensionally we one hot encoding strategy and the result is generating over 5,000 smart feature and creative noise. So in the future direction, we are we are replace one hot encoding with a compact technique like target encoding or entity embedding to reduce dimensionality. Thanks for your listening.